Welcome. It's my pleasure to introduce Dr. Neil Rowe. He's a professor of computer science. Let me check. Okay, my microphone is all right. He's a professor of computer science at the U.S. Naval Postgraduate School, where he has been since 1983. He has a PhD in computer science from Stanford University. His main research interests are in data mining, digital forensics, modeling of deception, and cyber warfare. He has also worked on text processing, computational geometry, and intelligent tutoring system. With further ado, let's welcome Neil.
Okay, great. Hope all of you can hear me. I'm on a committee at my school that's trying to decide on a new teleconferencing tool, and we started this long before coronavirus, so it was a very timely committee to be on. So we're trying a number of different things. We don't use WebEx, but we've been using 3 other different tools, and we're trying to decide which one to use. So I'm going to talk about digital forensics today, and in particular, our approach uses real data. So we're very interested in trying to find actual usage of computers and digital devices and see what people are doing on those devices. So it's similar to what field biologists do when they go out and observe an ecosystem. And they try to figure out what's going on in the ecosystem and what interactions there are. In the case of computers, this, of course, is not the usual approach in computer science. Mostly what computer scientists do is develop algorithms and protocols and things like that, and test them with particular training sets. But what I want to see is raw data and real training situations and things like that. And so we've collected a large collection of digital data that I'll explain about in a moment here. So we're going to use machine learning and big data processing. We're going to use a lot of different things to do that. And today I'm going to give you a sample of some of the projects that we work on. 3 research projects in particular. One is going to analyze the best places that malware could be on a computer system or digital device. One is going to look for patterns of updates to executables to decide what normal patterns are for executable updates so we can recognize abnormal patterns. And then I'm going to talk about some of the general background that I need to do these projects, which is excluding of uninteresting files. Digital forensics has been around for quite a while now, and it's basically technology for trying to analyze secondary storage. There are also digital forensic projects on main memory and on network data. My focus has always been on secondary storage because you've got a lot of things that are more permanent on the secondary storage, and they give you a better idea of what people are trying to do. So we have this wonderful test corpus that was developed by Professor Simpson Garfinkel, who's now moved on to the Census Bureau. And it's got about 4,000 drives in the collection. A drive is a copy of the secondary storage of a computer or a mobile device. And so we've got about 3,200 computers there, 400 mobile devices. And then I've also added to that my own collection of classroom and laboratory computers at the school, including some of our own individual computers. And they contain typically a lot of data compared to some of these other things because we have a lot of mobile things and also computers not very much used. So altogether, we got about 4,000 drives. Now, people keep asking me if they can use this. There are some obstacles to using this because there is private information on this. The way we obtained this, most of this data is we hired a guy to go around the world and go into computer stores and buy used equipment. And then once he got the equipment, copy the secondary storage. And sure, he found a number of drives that had been wiped or erased, but there was a surprising number of drives and devices that had not been erased. And as I've written in some of my work, even if you do try to do a factory reset on a mobile device, a lot of information remains on the mobile device. So we got quite a lot of interesting data from all over the world. The emphasis on all over the world was that there are more difficult restrictions with privacy if you work on data from U.S. citizens. And so we have to be careful with that. In addition to all the files on these drives, we also obtained some artifact data. We found things like email addresses, phone numbers, bank card numbers, personal names were also a big thing there, and keyword searches that people had done, URLs they'd visited, and things like that. But I won't talk about that today. So anyway, we're going to use a lot of basic machine learning. I'm not a big fan of using fancy methods in machine learning, so I'm not a big fan of using neural networks. I really want techniques that are easy to explain and easy to justify. So we've done a lot of stuff with naive Bayes reasoning, and we've done a lot of stuff with linear models where we just add up a bunch of factors and use those to decide things. And so we're going to use a lot of these methods for the three projects I'm going to talk about. Okay, so the first project we're going to talk about, we want to identify where malware is likely to be on a drive, because there are these things called quick scans that are often done to try to find malware, and we'd like to see if we can speed them up. Of course, to find malware, we can always do signature checking. It won't find truly new malware, though, so that's always the disadvantage of that. We could do static analysis, but it can make mistakes if it doesn't understand what it's looking at or somebody has obfuscated the code. We can do behavioral analysis, but you need a safe place to do that, and it can take some time, and also the malware may try to fool you. And then you can go on reputation of source, but you don't always know where it came from, or it may be spoofing, and also reputations can be bought. So there's a lot of problems in trying to analyze malware and try to do stuff. So the question is, can we at least get an idea where malware is likely to be on a computer system, or at least new malware is likely to be that we haven't already caught that's on our systems. And so pretty much every anti-malware vendor has a quick scan feature, and there's been very little study of whether these are actually checking the most likely places on the computer. So we attempted to try to get some evidence from our huge collection here, the 4,000 drives, of where the malware actually was. So in order to do this, we needed a blacklist and we needed a whitelist. And the blacklist is a list of things that are known to be malware. And so we've got 280,000 files in our corpus. And so we applied these methods to the 280,000. Or in the case of the fourth and fifth ones, to a sample of the corpus. The first thing is we bought a subscription for a year to something called Bit9 Forensic Service, which is a service that gives you blacklisting and whitelisting checking. So you can check to see if something's known to be bad or known to be good. And it's expensive, though. It was $50,000 a year. That's why we only did it for 1 year. And did a pretty thorough job. I'll explain something about where that came from and some other stuff in a moment here. Then we used two virus collections, one called Open Malware and, Open Malware and Virus Share. Virus Share is pretty well known. Open Malware was sort of an earlier version of that. And you can actually download the malware from that if you give them a good enough set of credentials for doing that. But we didn't have to download the malware. We got the hash codes. We got the hash codes of everything they had in their collection, and we matched them to the hash codes that we had on the files in our corpus. So we found how many items in the corpus we could identify. Our school uses Symantec, so we were able to run Symantec on a portion of the data, and same thing with ClamAV, which is a nice open source antivirus tool. Now, we were only able to do a sample because one of the problems with dealing with a corpus this large is it takes like 40 terabytes of data. So we can't store it in easily accessible format. So we have it on backup all the time. So in order to do these tests, I had to pull things out of the corpus, and that takes time. It takes time to actually go to the location in each one of these stored drives and pull everything out. So instead I took a random sample of these particular things. So they're not complete. But the first three things, we got a pretty complete indication of all the malware in a corpus. So altogether, we got about 300,000 instances of malware that we found in the 280 million files of our corpus. So the rate was about 0.1%. So we think that's probably pretty typical of a lot of users out there in the world. Of course, we didn't really take a random sample of users. We had we had more likely to have things from governments and business than we had from home users. But nonetheless, it's a good start to try to figure out what's going on with malware. Then the whitelists, Bit9 gave us a whitelist of executables that thought were okay. And we also use the National Software Reference Library, NSRL, which is a well-known collection of hash codes and other data for standard software. The way they get that is they hire interns every summer that download a whole lot of software for them, and then they compute the hash codes on it. But they don't run the software. They just get the static analysis of it in order to get hash codes. So they miss a lot of possible files you'd find on real systems. And then finally, we use for a whitelist a random sample of our corpus minus those identified as malware. As I say, it's 0.1% rate of malware, but if you exclude the known malware, we probably have a lower rate. So it's not a perfect way to get a whitelist, but it's probably pretty likely to work. And in particular, we're interested in things that are very common. For instance, we're interested in the common sorts of things that would be malware, and so we're not going to miss those by using that as a whitelist anyway. We're also, by the way, going to be using normative methods like Bayesian and reasoning and linear models. So those add up a bunch of factors and compute means and standard deviations. And so if you do that, the effect of including a few items of malware in your whitelist is not going to be very dramatic. Well, anyway, so here's my chart of the intersections of these various hash sets that we got. And the striking thing about this is when we put this together is that there's very little overlap between the malware detection methods, the 5 methods. If you look, for instance, at numbers, this is the Bit9 threats. It found 239,000 things in our corpus were labeled as malware by one of the by the Bit9 methods anyway. But if you look at for instance, virus share, there were only 28 of those that virus share had in its collection, and only 14 that 418 that open malware had. And you can also compare this, even though this is a sample for Symantec and ClamAV, you can see the numbers are real worrisome for this. Symantec found 1,434 things in our sample. By the way, the two numbers may indicate how many total instances were there and how many of them were unique instances. So there were 1,434 instances of malware identified by Symantec. 1,401 of those were unique. So anyway, but if you look at some of these other things like open malware and virus share, only 19 of those were found in the virus share collection. 289 were found in the Bit9 collection. So clearly there's a lot of disagreement between malware identification methods as to what is malware. They seem to be looking for different things. We have a foundation at our school, and I was presenting my research to the foundation, and there was a guy from Apple there, and so everybody turned to the guy from Apple and said, "Is this really true that security is this bad?" And he said, "Yeah, that's basically the dirty secret we have, that our security methods aren't working too well because there's not a lot of agreement between different methods for identifying what is malware and what's not malware." Here's some statistics on the rates. As you'd expect at our school, where we've got a firewall, the rates are pretty low, but a lot of this real data corpus didn't use firewalls and things like that, so the rates are higher here. So it gives you a little bit of idea about them, the overall rates of malware occurring in things. So here's our main results here. What we're trying to do is measure the number of standard deviations above the expected value for each of these clues that's listed on the left side here. And so number of standard deviations is assuming a Poisson distribution, and plus numbers mean that it's above the expected value, minus numbers means it's below the expected value, and you can see most of these numbers are below the expected value. So most of these were not good clues to malware. We tried some obvious things, including some standard things like whether we had a double extension, whether somebody had a file that was labeled, for instance, .exe, .txt, and a bunch of things like that, and those turned out not to be good clues. A few positive clues were things like, for instance, was it a deleted file? So these are standard deviations that go to the mean. 4 of the 5 methods agreed that being a deleted file was a good clue to malware. Of course, part of the reason something is deleted is your anti-malware may have deleted it automatically. And so that's probably the reason. Open malware disagreed, though. Interesting that there's little consensus between these methods in some of these cases. So we just took a majority vote on many of these things here. Rare extension turned out to be another good clue. Rare we defined as occurring only once in our collection. So any file in our collection of 4,000 drives that had an extension that only occurs once, that turned out to be a good clue that it was malware, which is kind of interesting. I have a second page here which shows some of the breakdowns for particular file extensions, top-level directories, and intermediate directories. And so this is pretty much what you'd expect. The executables did tend to be have a higher proportion of malware in them, and also security directories tended to have a higher proportion of malware, as you'd expect, because a lot of security directories contain quarantines of malware and things like that. So kind of interesting. It does confirm some of this, but again, you see a lot of negative numbers there, indicating that they weren't good positive clues. We can use negative clues too if we're trying to do quick scan, but we really want to know where the malware is hiding, and that requires positive clues. So here's a breakdown, a couple of graphs of malware fraction by size and depth in the file hierarchy. So you see there's a peak on the green curve which indicates size for relatively small files. So a lot of malware is pretty small. There's also a peak over here for very large files. This is the logarithm of the size, by the way. So this peak over here represents rootkits and other collections of malicious stuff. The blue curve indicates the level in the file hierarchy, and you can see that malware tends to not go any deeper than level 11, and so you could probably be pretty safe with anything below 11 in your file hierarchy. Number of drives on which a hash occurs. Now this turned out to be quite interesting because one of the things that intrusion detection systems and intrusion prevention systems are trying to do today is to increase their performance by bringing in something called reputation. So they're trying to say, how likely is it to be malware based on things like the reputation of the vendor or how often it occurs. And if they're using how often it occurs as a measure, this argues that they could be in trouble. Because you see there were quite a few things that occurred 18 times. This first peak is for 18 times. A bunch of things that occurred about 215 times, and a bunch of things that occurred 285 times. That's the number of drives that they occurred on. So they were spread all over, and yet they were malware. So I think it's questionable whether you can use popularity as an indication of whether it's safe to assume that it's okay and doesn't have malware in it. And but you know, people that are doing intrusion detection systems are pretty desperate for any way to improve things. They may be pushing too far, I think, on this. So anyway, we can put all these clues together to get a quick scan. Since we've got the number of standard deviations above and below the mean, we can turn that into a probability on a Poisson distribution and then compute odds. Here's the odds form of naive Bayes, which we used in our experiments. And so we basically got some recall precision and F-score values for these. We got a F-score around 250. The recall, as I'll argue in a little bit, is actually more important than the precision here. So that may not look so good, but if you just look at the executable files only, you're going to get an F-score of 0.0097. Not all that great. And so we're doing quite a bit better. So our method's got 5 times better precision with 1.7 times better recall over inspecting the executables alone. So even though quick scan seems like something really simple for a vendor to implement, they should put some more care into what they're doing when they do a quick scan, because it's not necessarily in the obvious places. One obvious thing, by the way, is we found many, many examples of malware in places that were not in executable directories. So malware is hiding all over the place, and you need to take that into account when you're looking for it. We also tested just looking at the operating system. That did even worse than looking only at the executables. Of course, you could argue that the operating system is more important, but you know, even if malware is in some unimportant part of the system, it could spread. to the operating system, and that's always the worry with malware. Okay, so that's the first topic. I'd like to move along here, and we can take questions at the end if you like. We've been studying lately executable patterns, patterns of executables when they get updated. And so what we were interested in was what changed between executables. Well, if you have the source code, you can look at the source code and figure out what they changed, but many vendors don't allow you access to the source code. So question is, can we do something useful with just the executables to figure out something was changed? If it's a small update, usually it doesn't change a whole lot of the executable, and we should be able to match up the parts of the executable that changed. And so we'd like to do this. Part of this is to figure out what the normal patterns of updates are and see if we can figure that out. And so when somebody does an abnormal update, we can recognize that. So anyway, we're going to compare bytes between files, and this work is quite simple-minded, and then we're just going to compare every byte of two files and see where they match up. And we'll try every possible way of matching up. What we'd like to find is a sequence, though, of bytes that matches to a sequence of bytes in the other file. And the more of those we can find, the more confident are we've found the mapping from one file's code to another. So here's an example of one of the displays we generate. The blue means things that match between two files. This spectrum-like bar represents one file, and the bar represents another file. And the blue means exact matches, consecutive matches that matched exactly between the two files there. The other colors, green, magenta, and red, represent matches at every second byte, every fourth byte, and every eighth byte. And the reason for that is, of course, there are 64-bit machines and 32-bit machines around. And so oftentimes, if it's just the arguments that change, the operands that change to a machine instruction, the machine instruction remains the same, and you can get matches on just the machine instruction. And so we were trying to see if we could find some of those. These particular files, though, didn't have a whole lot of those kinds of matches. They had mainly the blue, which means unbroken strings of all exact operands and operators in the machine code there. So pretty good. The white areas are areas that didn't match. So there was quite a bunch of data probably in this area here that didn't match at all between these two versions and could represent, for instance, different websites or things, different parameters that you're supposed to use in running this software. My student came up with an alternative representation where he actually showed which parts of one file connected to the parts of the other file that matched the parts of the other file. So this is a little messed up and hard to read, but you can sort of see that there were some things from right at the beginning here that matched some things towards the end of the other file, which is interesting. So we'll match up all these files. So what we did is we collected all the files in our corpus that had the same name, same file name. And we calculated their hash codes, and we picked one instance of each hash code, and those were our versions that we used for comparison. So there are really three kinds of different reasons why you might have a different hash code with the same name. Could be a software update. Since we've got a corpus that extends over quite a period of years, we can see the same file at different times on different computers, and we can see what the normal software updates are. They also could be different versions for different operating systems. So if that's the case, we're probably going to see the updates or the different versions all having creation times at about the same time. And then the third thing, perhaps the most interesting one, but the rarest, is that malware may have changed the file, or it may have been a Trojan horse to begin with. And so even though it's got the name of something that is a legitimate file, it may have quite different contents. And in fact, we found a lot of cases where of Trojan horses in this collection here. It didn't seem like malware authors were trying very much to conceal what they were doing when they gave names to files that were completely different and also a completely different size oftentimes than the original file there. Anyway, so here are two examples I want to show you of the plots that we can generate. The first one is a plot for hotfix.exe, and It's a file that that Microsoft uses for doing updates, quick updates and things like that. And you can see there's clearly patterns here where there are a whole bunch of versions that occurred almost the same time. So those are clearly versions for different hardware or operating systems. Another bunch here, similar to that. Another bunch of 3 here, another bunch of 4 here. So those are clearly the same, just versions for different environments of the same basic thing. Now the way this diagram works is that I drew lines between each version, which is a node, and the most similar previous version. And so there's a line always to the most similar previous version, and I computed similarity, as I say, by counting the number of sequences in common. So sequences had to be of 10 or more items in order to count. So you can clearly see there's a number of normal sort of software updates like bug fixes and things like that along these lines, but they're not terribly regular in the connection. So anytime you see things like that where there's quite a varying amount of time on the horizontal axis, that probably means that they were bug fixes of some sort. So what are these guys down here? These are probably mobile devices here, because these don't have any sufficiently similar item up here. So it looks like these were probably for particular mobile devices or some sort of specialized architecture. There were a few connections between them, but not too many, because they seem to be all pretty different from one another. So that's one diagram I want to show you. Now this one involves more malware. So this is cdfview.dll, which is a Microsoft executable. And you see that for a while there, it was going on pretty normally here. There were a couple of what appear to be bug fixes, because the slopes are different here over the time. But then all of a sudden, there seemed to be a lot of different versions here. So these different versions are probably all malware, because that's not a normal pattern for software vendors to create all sorts of different things and at equally spaced time periods. It turns out CDF-View is a particularly appealing program for malware to target, because you can use it to hide things in the operating system from people, and so there were quite a lot of attacks on CDF-View that we saw. Okay, most executables do have the same entropy pattern. So one of the things we want to do to improve this is to only match the parts of executables that are likely to be the most helpful in understanding what's going on, and that means the code generally. Sometimes the data can be interesting too, but code is the most interesting. Clearly the header is probably not very interesting. So you can look at a file by computing its entropy and see these parts of the file pretty obviously in the case of most executables. In this case, it looks like there were about 256 bytes at the beginning that have a relatively low entropy. So that's got to be the header. And then there was some code, and then there was some data, including some big blank areas in this data here. Probably the data is formatted so things start on even multiples of powers of 2. To find the stuff there. The entropy for the code, you notice, is pretty consistent here. We were using the average byte entropy on every 512 bytes in the file. So the average it goes up and down a little bit. You can have variations in 512 bytes, but there aren't too many. It seems to be hanging around 5.5 as the average value. So that's to be contrasted with, say, encoded or encrypted files, which tend to be 7.5 or so on the entropy. So you can clearly tell the difference between those things. And so I think what we'll do in the future is focus on using the entropy to guide us as to which parts are best to match. Here's another graph of some of the entropy values we had in our collection here. So there's a peak here that you can't see very well in the diagram right at 0. And as you'd expect, there's lots of 0 bytes in files on computer systems. With executables, often the 0 bytes are used because things are supposed to start at powers of 2 and other stuff like that. So 0 bytes you'll see an awful lot of. And the other peaks there's a peak here for text between 3 and 4. So these are text things embedded in the middle of, in other words, strings. strings embedded within executables. Then here's the peak I was saying, the between 5 and 6 for code. And then here's the peak for encoded and encrypted stuff within the executable. In most encodings, there are a lot of encodings, but of course the point of good encodings is that they try to capture the redundancy and eliminate the redundancy as much as possible. And so you typically, with many encodings, you get something that looks very much like encryption that's pretty high. And so that's probably what this peak is over here on the right. Okay, so the final thing I want to talk about is interesting versus uninteresting files. So we have a sponsor in the intelligence community whose name I can't give you, but they basically are interested in doing digital forensics on things that they collect from various parts of the world, like the Middle East. They've been doing a lot of stuff on trying to analyze terrorist groups in the Middle East and insurgencies and things like that are of military significance. They do a lot of work for the military. And so one of the problems they have is they have to do investigations very quickly. Oftentimes they're worried about a terrorist attack and they want to make sure that they get warning about a terrorist attack. So they're given days to analyze something important. And a lot of these things I've been talking about so far take long amounts of time to perform. You've got to if you're going to scan the entire drive, I don't know if you've used any of these forensic tools, but I use the autopsy tool a lot, and to load a typical drive, it takes like 12 hours or so, and do some analysis of it. So just getting the data up and loaded can be a problem. Just transferring it to one of these drives takes me 3 hours. Take something that takes 12 hours to process usually takes me about 3 hours to copy onto the drive where I'm going to do the analysis. So eliminating uninteresting data is a really critical issue in digital forensics. And so the sponsor had me looking at this and trying to figure out what to do. Now, I have mentioned the National Software Reference Library, and that's a good start. It can eliminate some of the things because they basically download all the major software in the world and install it on their computers and compute hash codes. So if you see those same hash codes, you can know they're probably unlikely to be interesting, even though NSRL and NIST that sponsors them don't provide a guarantee that there is no malware in their collection. But it's my experience has been it's pretty low probability. So question is, can we do something with the other files? Typically, NSRL eliminates 20% of the files on your drive, but when I've looked at drives in more detail, I think 95% of the files on a drive are typically not interesting for most forensic investigations. Now, there are really three kinds of forensic investigations. There are ones that involve criminal activity, so they're criminal investigations that police departments do and things like that, or civil court cases, anything legal. Then there's a second category that have to do with intelligence gathering, which is what my sponsor is interested in. And then there's a third category of applications which have to do with malware and maintaining security on computer systems. So for the first two categories, eliminating uninteresting data is important. It's also important with malware too, but the main issue is that you're going to need to at least do a scan of the entire drive at some point before you can start to focus on where the malware might be. Anyway, so we developed our own technique for doing this that eliminates a whole lot more files from investigation than NSRL does. And it uses these 9 criteria. Now, my sponsor likes the idea of things being binary or absolute. And so they didn't want me to compute a probability given these clues, but instead they wanted some absolute thresholds, and such that over the threshold it would be malware, below the threshold it would be okay, or above the threshold it would be interesting, below the threshold it would be uninteresting. So what our approach we developed was to say if the file matches 2 of these 9 criteria, then we're going to exclude it as being uninteresting. And I'll show you the results of our testing on our training set. Make it look pretty good, as the 2 out of 9 worked pretty well. So Criteria are frequent hash values, something that occurs many times in the corpus is probably uninteresting. Usually you're interested in things that are unique to the user of a single computer or mobile device. So things that occur a lot of time, probably not interesting. They could be frequent paths. They could be frequent file name directory pairs if they're being moved around in different paths in different operating systems. Another criteria is unusually busy times for a drive. If something occurs all at once, there were a lot of downloads all at once in one directory, that's probably an installation of software or an installation of a file that, a set of files that are probably not too interesting for you. And then unusually busy weeks in the corpus. When Microsoft does a major update, you'll see across our entire collection, a lot of people are getting that update within the same week. And so that's important to recognize that. And probably those are routine updates then. File sizes can matter. Also, sometimes there are certain file sizes we saw a lot of in the corpus because there are some fixed format files. So if you see those, they're probably uninteresting. Then contagion, if we've already found that most of the files in a directory are uninteresting based on the above methods, then probably any remaining files in that directory are also uninteresting by contagion with the ones that are there. Then there's paths that are from known uninteresting directories. Sometimes we just have to make up a list of things that are uninteresting, and including some files too. A classic example of that is the Jihad Handbook. There's a file that the sponsor has found many times in the Middle East, which is basically instructions on how to build bombs and create havoc in countries and blow up bridges and interesting things like that. So when they find that, that's quite interesting. So we need to have some lists of some interesting directories as well as uninteresting ones. On the other hand, if it's a game file, if it's a game directory, we're probably not interested in that. And there are quite a lot of game directories, as you expect in this collection, where we've just gone around the world and bought people's old computers. Same thing with extensions. Some extensions we know are associated with games, so we don't care about those. So here's some examples. Here's some same hash files. You can see that hashes can be quite helpful because there are all these different names for the same contents. Sometimes there's different names for the same contents because they're different languages, but they basically mean the same thing. So we want to recognize all the hash codes will allow us to recognize the same contents under a different name or different path. And then here's some of the same paths, different files with the same path there. Bottom level directory, a similar sort of thing. Busy times on the drive. We found a lot of things, for instance, on one particular Indian drive created on one particular day at one particular time. And so that's often a useful thing to, as a clue that is probably not interesting because that was probably a software installation. Now here's a graph of the entire corpus over a set of weeks there in the, I forget what time, particular set of time there, but it was, you can see there's clearly a huge peak here at this one particular week. And so that's clearly a Microsoft update. So any files we've got in that time period are probably related to the update. Of course, we'll have to check. You know, there'll have to be other clues. That's why we have the 2 out of 9 criteria, so we can find those kinds of things. But anyway, you can clearly see there's quite a lot of variation in the amount of activity in our corpus as a function of week of the year, and we should take that into account in deciding it's uninteresting or not. Frequent sizes, there's a lot of files with size 1691 for some reason. So it seems we're not sure exactly what they were, but it seems to be a standard format type thing. And here's some contagion examples. Here's some examples of some software files that we found and the directories they were in, and so we can recognize these directories and exclude anything from those directories. A lot of that was done manually. We had to go through and figure this out. And then we have some file extensions that we know are uninteresting. So we'll exclude all these files, and so here's what our results look like. We've got a whole bunch of files on our computer systems that and we've got 2 columns here, the number of files that we've got when we apply these methods, and then the number of distinct hashes that we've got. So full corpus when we did this test was 262.7 million files. We apply NSRL, we can knock that down to 200.1. If we look at the number of distinct hashes, it doesn't have as dramatic effect. It only reduces it by 6.6% for the reason that NSRL obviously tries to look at the very common files that occur many, many times. It doesn't have that many distinct hash codes. So anyway, then we applied our methods on top of NSRL, and we got it down to 21.4% of the original number of files. So that's a 2.5 times improvement on the number of files. And this is less work for forensic investigators. It's less work for your software that's scanning the drive. If you don't have to look at as many files, if you have to look only at 35% of, or 40%, I guess, of the files that are on the drive. So that's really impressive. We then had to add back some files that are interesting. I'll show you we had 6 criteria for interesting files that, and any caches that match those, we put back in, and the Jihad Handbook would be one example of that. We found the hash code of the Jihad Handbook. We put those back in. So we got pretty dramatic improvements, and the adding back the interesting files didn't add a whole lot of extra stuff. Didn't hurt our results too much. So it seems like this is a reasonable way to go, and it's really going to make an impact on our sponsor, because the sponsor has to do so much data processing in such short periods of time. So here's some examples of the recall and precision on this particular data here. So precision in this case means of all the uninteresting files that it labeled, how many of the things it called uninteresting were actually interesting? Recall means of all the files that it labeled as interesting, how many of those were really uninteresting? Now, if you think about it, precision is far more important than recall for us here, as it is for most security applications, because our sponsor doesn't want to miss the next 9/11, doesn't want to miss the next terrorist act. So if they fail to find, we failed to find something for them that was really important and relevant, that would be really bad. So you can see the precision values are quite high in the 0.99 range for most of these. The only two that are bad are this one here, the frequent sizes, and directory contagion, the contagion one. They're still not all that bad. This is 0.98, right? This is 0.98, so you only have a 2% error rate on that. So, but anyway, that's why we have the 2 out of 9 criteria. We try to have more than one clue before we decide something is uninteresting. Let me go back here. Yeah, so anyway, the recall isn't all that great, though. So, for instance, the recall varies quite a bit on these types of things. And what this means is we're getting a lot of false alarms. And we're getting maybe half false alarms on these types of things. But if you're familiar at all with intrusion detection systems, they get a lot of false alarms in intrusion detection systems. And so that's sort of an acceptable part of a lot of information security, that you're going to have a significant rate of false alarms. At least this is only 50%. A lot of intrusion detection data that I've seen has like finds like 100 times more false alarms than legitimate attacks on some of their systems. So I think this is acceptable performance for the system, and we're trying to implement this, by the way, right now. So I built a prototype for the sponsor, and they've now got a contractor who's trying to build them a production system so we can actually test this out and see how it works. Here's the interesting file clues. Now, interesting file is the stuff we put back in once we've eliminated by the 9 clues I just showed you. And so the only one that worked any good was the explicit lists of interesting extensions or directories. So the Jihad Handbook would be an example of that. We also had things like the sponsor told us, for instance, they are very interested in any software for permanent erasure of files. So in other words, something that writes over with zeros and ones, random patterns of the data so that you can't see what was originally there. I'm sure you all know that if you delete a file, it doesn't make it go away, and that's always been a great thing for digital forensics, is we can see a lot of deleted files and see what people were doing with the deleted files. And we got a lot of deleted files in our corpus that we can read. So anyway, we're interested in erasure. We're interested in anything that involves like penetration testing. We're interested in anything that to use to encrypt or encode things. Generally, encryption software that's not standard encryption software is very interesting. There's a particular package that's used a lot in the Middle East of encryption software, and so people are often using that one, and so we use that. Anyway, other methods that inconsistency between the extension and the magic number analysis. You often see this in forensic tools, but it didn't show to be too helpful. There were just too many false alarms. And then there were other things like hashes occurring only once for a given path, paths occurring only once for a given hash. And those turned out to be good. Nonetheless, I want to keep all 6 of these criteria because even though we didn't find them in our corpus, if we're dealing with data that's where people are being deliberately deceptive, you will find these things more often. People really going to efforts to be deceptive. I've written a book that was published in 2016 called Introduction to Cyber Deception. So I do a lot of work also on cyber deception. If you're interested, you can see some of my analysis with that. Okay, that's all I had to say. Any questions?
Hi, Neil. Great talk. I wonder if you have done cross validation in the first task where you try to find like what are the places where this malware will be installed. Because if you have the data set of all the malware, you probably can do simple static analysis. For example, you can just use grep to get all the directories, and then you can have a list of directories. And I wonder if you have done some, cross-checking between the list of directories you can find from the malware and the interesting directories you can find from the machine learning method.
Yeah, I'm not sure exactly what you're asking here. You're talking about the first project, right?
Yes, because I wonder if after your first project, you probably can point out like what are the most interesting like directories a malware wants to install, right?
Yeah.
So I assume you have a list of interesting directories you have for malware.
Well, all we can do is rate them as to the various categories they are. We have a hierarchy of directories. So we classify directories, so we use that classification to decide if something is interesting or not.
Yes, because then you have a list of directories which are interesting, because those are the places where malware are likely to get installed, right?
Well, we have categories. We have categories of directories, but it was the third project, which is the one that had a list of directories. The first project did not have a list of directories.
Oh, okay, I see. Because I was asking if you have a list of directories, then you probably could do cross-validation with the list of directories you can find using static analysis from the malware dataset.
Yeah, right. Yeah, that would be the hope. I basically just did the first step in trying to find malware, and there's a lot of more things you can do after that.
Gotcha. Thank you.
Okay, it looks like we have a question here from VJ. I'm gonna unmute your mic.
Hi, Neil. It was a great talk. So I just have a small question. Are these identification tools which you used and compared, like OpenShare, Bit9, and ViraShare, did you judge them to be the best in the market at what they do?
Well, they're what we could afford, mainly. We're researchers, so we don't have access to some of the really fancy stuff that some organizations have.
I understand.
So they were just a sample. ViraShare is pretty well accepted, so a lot of people are using ViraShare. Symantec is the one that's mandated for our school, so we had to do something with that one. And but as I saw, there are lots of weaknesses in Symantec. I mean, there were lots of interesting files that Symantec didn't flag that Bit9 was sure were malicious. And malicious in the top level, you know, Bit9 has several different levels of maliciousness, and so there were some that Bit9 was really sure about were malware that Symantec didn't find at all.
Okay. Okay. Thank you so much.
Hey, Mike, can you unmute Jack Zimmer's line, please? Go ahead, Jack.
Hi, I just had a question. You were talking about how you'd find a lot of game files, and I know that there's a big trend of terrorists communicating over game consoles, and using that kind of as a obscured medium to prevent forensic tools. Is there a process that you guys see in the field when working with that to extract that information?
Yeah, so we really need to rerun our testing to see if that's happening with some new drives to see if we find some instance of that, and that may change our opinion of game directories. Yeah, still
Great.
a lot of game
Thank
directories have files that are not going to be interesting, you know, there's going to be executables and things like that. There'll be configuration files. It'll only be a few files within the game directories that could possibly be interesting that we need to maybe re-examine.
Do we have more questions? Seems not. Thank you again, Neil. Really nice talk.
Okay, yeah, thank you for having me.
Thanks, Neil.
Great.
Okay, thanks, everybody.
All right. See you guys next Wednesday. Stay safe. Bye-bye.
Bye. Yeah.